Hello, my name is Armando Abrantes-Ferreira. I'm presenting my work entitled Comparative Performance Analysis of Grid Forming Strategies Applied to Disconnectable Microgrids. This work is co-authored with Professor Antônio Marcos Nogueira Lima. We are at the Department of Electrical Engineering at Federal University of Campina Grande, Paraíba, Brazil. I'm also an assistant professor of Federal Center for Technological Education, Cécilo Socorro da Fonseca, Cefet, Rio de Janeiro, Brazil. This is the agenda of my presentation. I will start with an introduction and motivation for the theme of my work. Then I will present the main aspects and difference for control of grid connector inverters. Then I will go into more details in the control of grid forming inverters, where I will discuss about conventional droop control and dispatchable virtual oscillator control techniques. And in this case, I'm going to propose a new dispatchable virtual oscillator control technique. And then I'll show the study system, which is going to be simulated in time domain simulation in PSIM, and then presenting the main conclusions of this work. To finish my presentation, I will show the reference I have used to make this presentation. First of all, we are facing an ever-growing need for electrical energy, and at the same time, we are increasing our concerns on climate change. One solution for that is the expansion of distributed generation, and most of this generation is fed by renewable energy sources, which are interfaced with the grid by inverters, which have some characteristic aspects. They are intermittent, they are scalable, they have faster dynamics when compared to conventional synchronous machine. They are computer controlled, so the dynamics of the generation units are defined by an algorithm, which reveals an opportunity to implement new ways for dynamics for these units. On the control of inverters, the first philosophy of control is called grid-following inverters, which are dispatchable current source because the control works controlling the output current of the inverter. In fact, this kind of control can provide primary regulation of frequency and voltage, but this regulation is indirect. Several works demonstrate that increasing this number of installations reduces the stability of the power systems. Another important point about these systems is there are no black start capabilities, which are related to the presence of the PLL, since this algorithm sends an already established grid to define the theta and omega reference for the inverter. Grid-form inverters, on the other hand, are dispatchable voltage sources. So in these inverters, the control objective is to define the voltage at the output of the inverter. And these inverters provide primary regulation of voltage and frequency in a more direct way, since the voltage and phase is directly defined by the control, which also provide the feature of black start capability. One important point about these inverters are their capability to provide damping to the grid. A challenge for these inverters are their robustness issues, since, for example, they still have problems with peaks of current during transients of loads and voltage. And also there are no grid codes for these inverters. Going into more details of the control of grid-forming inverters, these controls can be basically classified in two groups. The first one is the group of the controls based on the behavior of synchronous machine in different levels of abstraction. The main motivation for the development of these controls are their simple and intuitive implementation, since we have a lot of experience with the models and the control of synchronous machine. An important point is their compatibility with the legacy grid, since our current grids have their generation based on synchronous machine, so controlling an inverter to behave like a synchronous machine have a great opportunity for this compatibility. On the other hand, matching the behaviors of inverters and synchronous machine have some problems as they are different in their nature, which makes not clear if this approach is the best option for the control of grid-forming inverters. The second group is a group of the control based on virtual oscillator control, which emulates the behavior of nonlinear oscillators. They have time domain implementation, which make them faster when compared to control methods based on quasi-steady-state behavior. A very interesting point about these controls is their almost global synchronization, which comes from the theory of synchronization of network of coupled nonlinear oscillators. And also they embed droop control law close to steady state, which is mandatory for the compatibility with legacy grids. But they have nonlinear droop behavior, which is not clear if it's the optimal behavior for sharing power. And also they present coupling between active and reactive droop relationships. Conventional droop control is the baseline solution of grid-forming inverters, and it's based on the quasi-steady-state behavior of the conventional speed droop control of synchronous machines. They are based on these quasi-steady-state relationships. In the case of low-voltage networks, which are mainly resistive, the droop relationships are linear between voltage and active power and frequency and reactive power. And the tuning criteria is based on the steady-state operation points of the inverter. And the tuning is defined as the ratio between the maximum deviation at steady state for voltage and the rated active power, or the gain related to active power droop. And for the gain in the reactive power droop, we have the maximum frequency deviation over the rated reactive power. The unified virtual oscillator control is a dispatchable virtual oscillator control method. A very characteristic point of this control is that it only uses the output current of the inverter as an input for the control. And this control is based in regulate a voltage of an internal oscillator model. And this regulation is based on this equation 3, which have a term for regulating the amplitude of this vector V alpha beta and a correction term related to the output current. And this reference for output current embeds the reference for active and reactive power. So this last term here is related to the regulation of the power itself. We have 3 control gains to define in this control, which are mi, the voltage error gain, eta, the current error gain, and phi, which is defined as the equivalent impedance as seen from the point of coupling of the inverter. At steady state, this control presents this droop relationship, which is nonlinear for active droop, and it's linear for reactive power droop relationship, but has a coupling with the voltage. The tuning criteria for this control is also based in steady-state operation points, where the eta gain is defined as a function of the maximum frequency deviation, the maximum voltage deviation, and the rated reactive power. The min gain is defined in terms of rated active power and maximum voltage deviation, and also with the reference voltage. In this work, we propose a new dispatchable virtual oscillator control, which also only uses output current as a measurement for the control, and has the following control law. It has the same structure as that of unified virtual oscillator control. The sigma gain is related to the voltage error, and rho gain is related to the error of output current. A very important point of this control is its linear droop relationship, which has a behavior closer to conventional droop control, and brings the advantage of a simpler tuning criteria, defining the rho gain as the ratio between maximum deviation of frequency and rated reactive power, and the sigma gain is related to maximum voltage deviation and rated active power. To compare the performance of the 3 studied grid-forming control strategies, we'll study a low-voltage disconnectable microgrid through time-domain simulations in the software PSIM, where we have 2 identical grid-forming inverters, which are parameterized to have reactive droop coefficients set to 1% and active power droop coefficient set to 2 distinct scenarios, one of 2.5% of maximum voltage deviation, and we have an adjustable resistive load with the rated power of 2.2 kilowatt. And as we have these circuit breakers, we have different scenarios of test where we can operate with the microgrid connected to the grid and also in isolated mode, and we can have 1 or 2 grid-forming inverters operating in parallel. And this is the parameterization of the system. And these are the control parameters for each control method for the 2 distinct maximum voltage deviation scenarios. First, we have the steady-state results from the test of the microgrid operating in isolated mode with only 1 grid-forming inverter for the case of the inverter being controlled with unified virtual oscillator control. For the 2 scenarios of voltage deviation of 2.5 and 30%, considering only 1 grid-forming inverter feeding the load, and we have as dashed pink line the analytical curve for the active power droop relationship, and we have the blue line as the droop relationship considering output power and internal module voltage, and the red lines as the relationship of output active power and the converter output voltage. First of all, we can see in the curve that when we compare the blue line and the pink line, we can see that there's an offset which doesn't affect the analysis here, because the main point to analyze the droop relationship is about their slope, and we can see that the blue lines are parallel with the pink lines, which reveal that in fact, considering the internal module voltage, the droop relationship actually followed the design. But when we look at the red line, we see that the active power droop relationship doesn't follow the design curve, which can bring problems in regulating active power of the inverter. Also, you can see that these deviations of the blue and red lines are the same for 10% and 2.5% regulation, but it's important to highlight that this deviation of 1.15 volts is stronger when compared to design deviation of the case of 2.5%. And these are the steady-state results for the same operating scenario for the microgrid, but in this case, the inverter being controlled by the proposed linear droop dispatchable virtual oscillator control. We can see that comparing the blue lines with the dashed pink line, we can see that they are parallel in the sense that they have actually the same slope. So the design was accomplished when we see it in terms of internal voltage module, But when we see the red lines, which are the active power drop relationships considering the voltage at the converter output, we can see that there is a deviation between the blue and red lines. We can see here a similar behavior as the unified virtual oscillator control, but this deviation in this case of 2.5% is bigger when we see the design voltage deviation. And then we have the steady-state results for the same scenario of islanded mode with only one grid-form inverter feeding the load. But in this case, we have the results for conventional droop control, unified virtual oscillator control, and the proposed linear droop dispatchable virtual oscillator control. But all of the results are in terms of the output voltage of the inverter. So we can see that the dashed pink line is the design and droop relationship, and we can see that the droop control followed very well this relationship. The unified virtual oscillator control and the proposed linear droop virtual oscillator control have very close behavior and both present nonlinear relationships. And from these results, we can see that the active power relationships of the dispatchable virtual oscillator control techniques are related to internal virtual oscillator model. And it's interesting to point out that when we consider the relationship between active power and the voltage at the output of the inverter, both dispatchable virtual oscillator control methods presented similar results. On the other hand, conventional droop control had presented the best results when you take into account the achievement of the design and droop relationship. Now we will look at the transient results from the test of the islanded mode with two grid-forming inverters connected in parallel feeding the resistive load. And you can see in this figure the active power over the time. In the first time interval, you can see that the operating point for the inverters controlled by dispatchable virtual oscillator control are really similar, which are slightly different from the inverter controlled by conventional droop control. And the first transient, we can see that in the first moment, the three control methods present similar results. But as the time evolves, we can see that conventional droop control is much slower than virtual oscillator control, where the setting time for this conventional droop control is about 8 times longer than for the dispatchable virtual oscillator control methods. We have similar results for the next transients and we finish coming back to the initial load. Now we have the transient results for the case of the microgrid operating in grid-connected mode, in this case with only one inverter connected to the grid and feeding a load, and it's going to happen the same load transients as in the last test. We can see that the regulation of active power for conventional droop control is very poor, and when we compare to virtual oscillator control methods, we can see that they have very close operation points, and for the first transient we can see that they have the same behavior at the beginning of the transient, but as the time evolves we can see that the conventional droop control takes much longer time to settle. And also you can see that the dispatchable virtual oscillator control operate at closer operating points and with lower ripple when you compare to conventional droop control. We have a similar result for this response in the next transients, and you come back to the original set point of power for the load. From these results you can see that the dispatchable virtual oscillator control methods presented similar response in transients and the steady state points of operation. Also, the dispatchable virtual oscillator control presented overall superior performance when compared to droop control when you look at the settling times for active power in both grid-connected and islanded modes. And another important point is that the dispatchable virtual oscillator control presented better humidity for ratios different from ideal poorly resistive output impedance. So in this work we have proposed a novel linear droop dispatchable virtual oscillator control, and we have qualitatively compared to the conventional droop control and the unified virtual oscillator control in a low voltage disconnectable microgrid setup through time domain simulations in PSIM. From the results, we have confirmed that the dispatchable virtual oscillator control techniques have the active power droop relationship related to the internal model voltage, so that the active power droop at the output of the inverter is not defined at the control objective, which can bring errors in active power regulation. In this sense, conventional droop control presented better results when we take into account their capability to regulate the active power following the designed active power droop relationship. And when we look at dynamic response, we found that the dispatchable virtual oscillator control methods presented similar response and both showing superior performance compared to conventional droop control, which is expected as the conventional droop control is defined in quasi-steady state quantities, while dispatchable virtual oscillator control methods are based in time domain implementations. Another point about dispatchable virtual oscillator control is that they presented better results for the humidity to operation with equivalent output impedance different from the purely resistive lines. And for future work is indicated the study of the reformulation of the control problem of the dispatchable virtual cellular control to define the group relationships at the output of the inverter. And also is indicated the study of comparative analysis between the proposed linear group virtual cellular control and other virtual cellular control techniques for scenarios where the effect of the power loops couplings are significant. As in this work, this was not explored. And these are the references of my presentation. And thank you very much for your attention.